All right, here we go. What we got here is some real world math, some big boy and big girl math. Okay, let's go, let's go. So if you look here, we're doing right triangles in the real world. And in this problem, we're given that the high school, White House, and then Reagan National Airport form vertices of the right triangle. You can see here, here it's White House, and that's the airport. The angle between the direct path from the high school to the airport, so that'd be something like this. They're saying is 28.7 degrees. And then they tell us the distance from the White House to the airport is 5.15 kilometers. And if we look on the next slide, we see that here. So here's our angle, here's 5.15 kilometers. And if you look, here's our big triangle. And then always start your angle, circle that and say, oh, look what I got here. Oh, that's opposite. A here is adjacent because it's touching it. And it says it wants us to find how far is the high school from the White House. So they want X here. And how far is the high school from the airport? They want Y here. And so let's start by finding X. So X is the hypotenuse H. And we have the angle 28.7 degrees. We can form this equation here by using O and the angle like that. So we have the angle, so it's sine of the angle because it's opposite, and we're looking for the hypotenuse H right here, which is X. So it's the angle, sine of the angle equals the opposite over the hypotenuse. So for this one, we want to get try to isolate the X, so we got to multiply both sides by X like that. And so if we do that, then the X cancels on the right side, and we're left with this. X times sine 28.7 degrees equals 5.15. X is still not isolated, so we're not done. Got to divide both sides by 28.7 degrees, or sine 28.7 degrees. So we get this. We divided both sides by sine 28.7 degrees, like that. So that's why this cancels out over here. Go away. We don't want you no more. X is by itself now. Tee-hee. So now we have X equals 5.15 over sine 28.7 degrees. Put that in the calculator, and you will get 10.7. So what that's telling you now is that our hypotenuse, or X, the distance from the high school to the White House, is 10.7. And I'll put that up there like that. You see that? So our hypotenuse is 10.7. Now they still want us to find Y. We have a right triangle, so we have this right here like this. We've got 10.7 here, 5.15. That's our right angle. We're looking for this guy here. Oh look, we can do this. A squared plus B squared equals C squared. So we'll say 5.15 squared plus, we don't know Y, so I'll put Y squared equals 10.7 squared. Now remember, I put 10.7 as C because this is the longest side. C has to be the longest side, which is opposite of the biggest angle, our 90-degree angle. So all we do is we subtract 5.15 squared from both sides, and we get Y squared equals 10, sorry, it's supposed to be squared as well. 10.7 squared minus 5.15 squared. Then we do the square root of both sides, and then we can put this whole thing in our calculator. And when we do that, we get the answer is 9 point nasty. So I'll put it in 3 sig figs, 9.38 kilometers. Again, this is an example of a real world problem, but if you see, the very basis of it is what we've already learned, which is the trig functions, the trig ratios, and Pythagorean theorem. Next problem. So here we have two new terms when we're talking about real world problems. We have angles of elevation, angles of depression. So look at our little bird here. Hey, little bird. All right, so this little bird is flying in this direction and is looking down at the building here. You see this is his eyesight down at the building. So the angle of depression goes from the horizon, the direction he's going, and it's between the direction he's going and his eyesight. So if you see here, we'll say the angle between the horizon and a line crossing below it. So this line below it is its eyesight. This is the angle of depression. Angle of depression is between the horizon here, so this blue line, and the red line. Angle of elevation goes the opposite direction. Look at this man right here. So he's going this way, walking to the tower, but he's going to look up to the top of the tower, and that's going to be his angle of elevation. See? That's his eyesight. He's going from here, and he's looking up at the top of the tower. A good example of this would be, so for example, if the bird's up here and the man's down here, if they're walking and their eye lines meet, the angle of depression and elevation is going to be the same, because these two lines here, this one and this line are parallel, which means that this one line that's in between them creates equal angles. These are alternate interior angles. You learn this in geometry. Alternate interior angles are always equal. So if I find one of these angles, I know the other one, and that's only if they share a common line between the horizons. And so the next slide will give you a good example of this. So look at this. A pilot is making his final approach to the runway from an altitude of 500 feet. So we have a plane here. Here's my plane. I don't know why I'm making these sound effects. Okay, so our plane is what, like 500 feet? That's the altitude, so this is what, 500. And then the landing point is down here somewhere. It's going to land over here somewhere. And it says he is 9,540 feet away from the landing site, say L. And the plane is traveling this way. So a good representation of this would be a right triangle, and you'll see that here. So here's a plane up here. It's 500 feet off the ground, and it's 9,540 feet away from the runway, and it's traveling in that direction. So this is the angle of depression, because the plane is going this way and it's moving down that way gradually. That's the angle of depression. So if you look at that, don't they share a line? They share a line right here. So that means the angle of elevation here is the same as the angle of depression here. So if I can find this, then I'll know what this is. So I can look at this and say, oh, look, opposite, that's O, over hypotenuse here, H. That is so, so, ka, toa, don't forget. We're doing this because it's opposite over hypotenuse. And when we set it up, we'll get that, opposite over hypotenuse. And so this we'll have to use inverse trig because we're looking for an angle measurement. So when we put this in the inverse trig function in the calculator, we will get 3 degrees. So then that means this is 3 degrees. And also this is 3 degrees. One more example. A 14-foot ladder is used to scale a 13-foot wall. So, a ladder, if you have a wall here somewhere, and let's say you're trying to, I don't know, jump onto somebody's roof, because that's what people do for fun. So we're going to have this like a 14-foot ladder. This is a 13-foot wall. So it says it wants to know the angle you have to put the ladder at. So you're going to have something that looks like that. So 14-foot ladder, it's a 13-foot wall, and this is the angle you're looking for. So I'll say, okay, look at that. Isn't that opposite? And then this is the hypotenuse here. So then I'm going to use sine here. So I'll say sine is 13 over 14, which is what? Oh, that's my opposite. This is my hypotenuse. Now, to get the angle measure, I have to use inverse sine. So I'm going to put this into the inverse equation right here like this on the calculator. And then I'll get that 68.2 degrees.